Okay, welcome back. So the first speaker this afternoon is Gabriel Fazoli, currently doing his PhD here at IMPA, and he will talk about canonical extensions of partial connections.
Okay, thank you, George. Thank you, the audience here and in French. So the title of my talk is Canonical Extensions of Partial Connections, and the main goal here is to construct connections. Construct partial connections. Okay? First, I will explain what is a connection for those who don't know. And we are working the following set. Let's X be a complex smooth variety. And let E be a coherent sheaf of OX modules. Okay, so we are fixing this setting. And a connection is a morphism. Let me write it here. A connection is a C-linear morphism from E to home of, sorry, let me give first the usual way to write it. Is a C-linear morphism from omega x to tensor E. This is the same as home of Tx to E. In fixing notation, take a section here, take a vector on Tx, and you derive it. And you write this. Okay, just fix the notation. C-linear and satisfies the Leibniz rule. This means the derivation of a product of a function by a section of E is the derivative of f times s plus the derivative in s. Okay? And the idea of connections is to generalize the concept of derivation. Here, when we define a connection, we are giving a rule to derive a section of a sheaf. Okay? So this is what connections is. And now I will define partial connections. Okay, first, let's remember that a foliation F is a subsheaf of Tx that has two properties. First, it's closed by Lie bracket. And second, the quotient of this is torsion-free. Okay, this is a foliation in your sense here. And given a smooth variety X, as I have written, a sheaf A and a foliation F, we can define a F partial connection in E. Okay? So I will define a F partial connection as before, a C-linear map from E to home of Tf to E. Okay? And fixing notation again, take a section here, take a vector on Tf now, and send it to this symbol, okay, such that C linear and satisfying like a Leibniz rule. The derivation of the product of a function by a section, the derivative of the function plus function times the derivative of the section, okay? The difference here is that we don't know how to derivating every vector of the manifold. We just know how to calculate the derivative of a section in directions tangent to the foliation. Okay? One more concept that I will give here is the concept of flat partial connection. So, nabla is flat if nabla of the Lie-Bracht of two vectors on the tangent of the foliation is the Lie-Bracht of the nablas. Okay? So this is flat connections, flat partial connections. And I will give two examples. First example is the derivation of functions. This means we take we take the sheaf of functions on X. We apply the derivation to the cotangent of the variety. And then, as we have the inclusion of the tangent on Tx, we have here a natural dual morphism from the cotangent of the variety to the dual of the tangent sheaf of the foliation. Okay? And I will denote this map by df to remember that we are taking a foliation here. And it's easy to verify that df is a flat partial connection. Okay? A second example that appears naturally in this theory is the bot connection. Okay? And the bot connection is constructed like that. First, we consider the exact sequence of the inclusion of Tf on Tx, and we look for the quotient of this. Okay? The bot connection is a connection defined on this quotient. Okay? This morphism is surjective, so every time we want to take a section here, we can consider a pre-image here on Tx. We consider the bot connection on this quotient as a map that takes a section on this quotient and send it to take a vector on Tf, make the Lie bracket of this section with this section, and then push it to the quotient again. Okay, and one can verify that we'll define it, well define it, and nabla bot is a flat partial connection. Okay, so two natural examples of flat connections, flat partial connections. So I will put here a question. Why study flat partial connections? A first reason that I'm giving is because the existence of flat partial connections give to us numerical properties of a sheaf. So, numerical properties. Okay, and this is work. There are several works by Baum and Bott in this sense. Okay. A second reason is because we can use partial connections to describe geometric structures. For example, a much better way to define a transversely affine structure on a foliation is with means of a partial connection, with the Bott connection. So, for example, it's used to define transversely affine structures. Okay? And a third reason is because, in some sense, flat partial connections are sheaves on the space of leaves of the foliation. Okay, so in some sense we can use flat partial connections to study the geometry of the space of leaves. Okay. Given all that, I will propose a problem here. And the problem is the follows general problem: find partial connections. Okay, I can give you a easy way to find new partial connections. Suppose that you are given a set of partial connections. So, given partial connections. One thing that you can do with all these given partial connections is to consider constructions from linear algebra. You can consider tensor, wedge, sim, home, all these collections of constructions, and this gives to us new partial connections. Okay? They are good, but they are not enough. They do not generate all flat partial connections from just these constructions. For example, I will put this question here. Consider a foliation of codimension 1 now. Is there a flat partial connection on a rank 2 flat partial connection on a rank 2 sheaf that is indecomposable, so such that it is not the sum of flat partial connections. It's not the sum of flat partial connections on rank U sheaves. we cannot answer this just with this kind of constructions. So here we are going to give a partial answer to this, at least. So here we are presenting a solution. Not a complete solution, but a construction. We are presenting a construction here of a rank 2 sheaf that will not be any sheaf. It will be a geometric sense in this sheaf. And we put in this sheaf, we show that this sheaf admits a flat partial connection. Okay, so let's do this construction. Okay, in this construction, it can be made more general, but I will consider a codimension 1 foliation and a flat partial connection on a line bundle. Okay, for example, OX, the body connection are examples that we can apply this construction. First, we consider the sheaf of differential operators from L to OX. Okay, I will explain what is this. First, this sheaf is a subsheaf of C-linear morphisms from L to X. Okay, so our element here is a C-linear morphism, but such that for every function we take this composition is OX linear. Okay? And if we take bases from L and from a coordinate set for the variety, this corresponds to differential equations, right? Derivatives of first order. So take this sheaf. And now we are going to do the following remark. Every time that we take a vector on TF, given the connection, the flat partial connection, this that comes from L to L, okay, this is a differential operator of order as equal 1, and we take phi as a OX morphism from L to OX. Then the composition of phi and nabla V, it's inside this sheaf. Okay? So these are elements here. And given these elements here, we can take this submodel. We define the submodel of sections like compositions of OX morphism with derivations in vectors of the tangent of the foliation. Okay, so we take this inside the shift of differential operators. Then we consider the following. We consider the quotient of this. We consider the quotient, I will denote the quotient as, and I will explain better. This I will denote by this because it has a property, this one. Given a flat section of the partial connection, given two differential operators here, such that they have the same image here. Then they do the same thing on this flat section. Okay, it's not hard to verify this. And this is a reason to consider this as a shift of differential operators of order at most 1 on flat sections of the partial connection. Okay? So this shift has this interpretation here. And in this case, is it to verify that this one has rank 2, okay? And this will be the candidate to have a flat partial connection. I will do an example of this, a very easy one. Example, if one starts with the derivation on the shift of functions, what we get, we are just taking TF inside TX. Okay, in this case, differential operators is TX plus OX. And here we are just inputting the vector here inside TX. And the quotient is like this. Okay, so okay, so theorem. If you take a codimension on foliation, ele enabla flat partial connection. Then this shift that we just constructed admits a flat partial connection. And this connection is given very explicitly. I will write it here. The connection is given like we take a derivative, a section here that the image of a differential, and we send it to given a vector here. We do a decomposition of V with this differential operator less the differential operator with nabla V. We do this in the sheaf of differential operators, and then we consider the projection back here. So this is a flat partial connection in this sheaf. Okay? So for example, when we do this with, and this, well, we need to verify that it will well defined, that's linear, satisfies Leibniz condition, it's flat, all these kind of verifications. So the proof of this theorem is just verification. For example, if we start again with our connection here on derivation of functions, the construction gives to us partial connections that is the bot connection plus, again, the derivation. Okay, so in this sense, this construction generalizes the construction of the bot connection. Okay? Right. And now I will make a proposition that partially answers the question that I did before. Let F be a codimension 1 foliation on a complex variety as before. Suppose F is not given by a closed metamorphic one form. Then, well, this is the only assumption that we're making. Then the shift that we make from the bot connection is indecomposable. Okay? So yes, so in this case we have a shift that is not the sum of two linear shifts with partial connections. Okay, so this answer partially. Just to make some remarks, we make here a construction. Well, we suppose that F has codimension 1, and we did this with flat partial connections on a line bundle. But we can start with a flat partial connection in for example, a reflexive sheaf, any rank, and it takes to us the very same construction for every k of a sheaf of order k, of differential operators of order k on flat sections of this nabla, and this admits a flat partial connection for every k. Okay. And a very interesting object is the dual of this. The dual of this is a sheaf of jets of flat sections of nabla. And this is a very interesting sheaf, and we are work in progress is to use this sheaf to give information about the foliation using this sheaf with this connection. That's all that I have to say.
Thank you very much, Gabriel. Are there questions here or there?
Questions?
We have two here.
So, I would like to ask about this construction for higher K. So, is there the same question you gave about the decomposability? Can you use the same construction to obtain an example which is indecomposable?
Yeah, I didn't stop to think about this kind of question, but I would expect always that you have a very, because to be decomposable is very strong in some sense with this sheaf, and I would expect that if we have this kind of decomposition, we can find some property about the foliation, but I don't have the answer in general.
And the construction of these connections is like passing through this eye of nebula you define. It's the same construction.
Sorry.
How's the construction of this for a higher K? So it's very similar.
It's very similar. You consider this. You consider this kind of sheaf. Yeah, it's very similar. So, but we want a subsheaf of order K instead of 1 here, and so we instead of consider home from L to OX, we consider differential operators of order K less 1. So the composition is our order K differential operator from L to OX. And we take quotient and we take a connection like that, like the Lie product of V and the differential operator. Very similar.
So is it an if and only if, that proposition? So what happens if it's given by a closed one form?
I don't know. Yeah, I cannot think at a counterexample now, but I don't know.
We have a question here
Okay, please.
by Chris Lane.
Hey, Fazoli, I have a question. I didn't understand well the connection between the connection that we have and the leaves of the foliation. For example, if you have a connection that is written that nabla 1 plus nabla 2, what is the properties on the leaves of the foliation?
You are talking about the initial reason that I gave for the construction. I didn't understand. Sorry.
Yes.
So the object partial connection is like a family of connections on the leaves. And what he was saying is that this flatness condition can be interpreted as descent data to the leaf space. Even if the leaf space does not exist, these objects could be thought as living on the leaf space. But yeah, from just general nonsense, you cannot get information from the leaves directly. I don't think, at least I don't know how to do that.
Okay, thank you.
Okay, so thank you, Gabriel. There is no other question?
And here, I don't think that there are
Here?
neither. So let's thank him again.
Thank you.